Can you hear me? Yes, I can feel like a pop star. Okay, so I'm going to talk. So this is going to be more or less like an introduction to this session, I think. I'm going to talk about generative models as priors in signal processing. So the classical idea that we heard earlier is to just exploit the structure of the signal for your signal processing. In typically, the signals that one wants to use, for instance, natural images, have some intrinsic structure, like natural images in the 90s. Ingrid Devishis realized that natural images are sparse in the wavelet basis, and then early in the 2000s, the whole field of compression sensing exploded, and they exploited the sparsity structure for signal processing in a very successful way. I'm not going to explain compression sensing, but just going to say that you can get away with having fewer measurements that you would need for reconstructing images if you exploit the structure, like the sparsity structure. Like here, if you want to do some reconstruction without using the sparsity, you are losing a lot. But now we are moving to a different era where everyone wants to do deep learning and wants to learn the structure of the signals, wants to learn what their algorithms, wants to learn to do things. And so in particular, for signal processing, one will want to learn the structure of the signal. And this is what this session in this afternoon, I think, is about. So I claim that generative models are the new sparsity in this field. And generative models have existed in many ways. Like mixture of Gaussians is a generative model that people use all the time in theoretical computer science or for assumptions for your noise, etc. But here we're looking into data-driven generative models, where basically what one wants to do is to learn a low-dimensional parametrization of your data or learn the probability distribution of your data using some learning algorithm. So in particular, we heard earlier about autoencoders. There's also the generative adversarial networks. There's many kind of architectures that one can use to learn a generative model that in this case is going to be a function that depends on some parameters that one can learn. And given some noise, you evaluate this function in some noise, and then you get something that looks like real data. Actually, ideally we want to behave like the data distribution, but in practice, it's not known whether you can achieve something like that or if how one would go. If this is a very hard engineering problem and also a theoretical problem, like how can one get something like this? There's also other structures that people use that require no training, like this deep image prior and deep decoders, that basically they have some form of generative, like they have some sort of structure that can encode their data and not their noise. And they use that for signal processing as well. So this example from this paper by Jitendra Malik, who is a professor here, they have this very sophisticated infrastructure from Facebook, where what they do is they train a generative model for faces, and all these images here are just like G of some noise. These people do not exist, and then for G of every possible value of noise, then you get a face. That's like the typical way of showing how successful this thing can be. Okay, so I am a mathematician, so my examples are going to be more humble. I'm just going to go with the handwritten digits data set, and in order to explain how this can work. So I have this data set with digits. I add a lot of noise, way more noise than people can use in like classical signal processing. And then I'm going to do denoising. So the classical algorithm of shrinkage in the wavelet domain can produce something like this. They pick up a lot of noise, like extraction from the noise, because there's so much noise. If you use total variation denoising, you get something better, but still there's a lot of things that gets picked up in the noise. And then what I do here in my laptop, it's just like I train a generative adversarial network to produce a generative model for this data set. And I do the denoising by finding the nearest point in the image of my model. And then what I get is like very, very good denoising. If you look at this 8 and this 8, they don't look exactly alike, but they are the same thing. So you can think of this as a good proxy for understanding what is the structure of the model that you care about. And so the classical setting for these generative adversarial networks is I consider linear composition of linear, like just feed-forward neural networks. It's like a linear function with a nonlinearity activation, several layers of these, very simple. And then I train two neural networks, one against each other. One is going to be the discriminator that learns to decide whether an image is real or fake, and then a generator that, given some noise, it produces an output that is going to try to fool the discriminator. And I train one against the other one. So that's like the classical setting from the generative adversarial networks. And that's basically what I did. The training loss has this form. That is basically what I just said. And this has a problem that is called model collapse, that you can have that you don't express your whole space. Like when I trained it, at some point I got this. This is not, it only expresses like ones and maybe twos or eights, I don't know. So that's something that one needs to take care about. And basically the denoising, how do I use this generator for denoising? Is I look at the closest element in the image of my training, of my generator. So this is the very simple denoising, the norm that I use. I mean, there's many ways to do this, but basically the idea is that. Also, so here I'm kind of assuming that I'm training with some data set that is of real images. If my data set is noisy, that can also be incorporated into the training set. This has been done in many ways. One way of doing it is like say, okay, my discriminator is going to look at noisy data. So then when I train the discriminator with the output of the generator, I should also tell him what the noise should look like. So the noise is not what allows the discriminator to decide whether the thing is good or not. And in order to do something like this, we need to have a model for the noise, which is not something that we can always have. But actually, I did this example, training with noisy data. And if I take this out, or if I leave it, I obtain more or less the same results. And actually, it seems like I can learn the quite decent generative model without having a model for the noise or just from noisy data. And it's not obvious to me why, but there's some ideas in the literature that can tell me maybe why can this be possible. One idea is that there are some architectures that cannot express Gaussian noise, and what I'm using is Gaussian noise. So maybe this is going on. But, okay, let's see. How much time do I have? Okay, so, so basically my idea to start working this problem was from a theoretical point of view. I wanted to see what kind of theorems one can prove about this. And there is this result by Alex Dimakis, who is actually in the Simons Institute right now. There's like a deep learning thing going on. And what they show is that you can solve the compressed sensing problem with 10 times fewer measurements than classic compressed sensing, and they have some theoretical results. Like if you solve some sort of optimization problems, you have guarantees of finding the solution of the compressed sensing problem. And then there's this paper by Paul Hahn and Vlad Boroninsky when they show that if you have a random neural network, then the optimization problem is easy. And so what we do is we consider a simple toy model, and we analyze what kind of activation functions, what kind of properties the activation functions should have in order to be able to do denoising with these models. And it turns out, I'm not going to go into the details of this, but it turns out that there is nice properties that you can analyze the activation functions using the spherical harmonics, and then you can have nice properties for that. But in what is relevant for this workshop, I think, is like the application of this setting to an astronomical problem. In particular, we were going to use, we're going to try to learn a generative model for stellar spectra. In particular, we have a data set that has like 40,000, that comes from 40,000 stars. We have the flags of each pixel for every value of different wavelengths. That here is a high resolution image. And we train a generative model to produce maybe a generative model for this kind of data. And we want to see how can we validate this with other generative models in order to see whether these fake stars that we produce have realistic properties or not. Can we validate it in that way using the canon for the model, the canon model for validation? And can we use this for signal processing in this kind of field? So this is it. This is more or less what I wanted to talk about. So generative models are powerful priors for signal processing. We're going to see this in the next talks here. They can be learned from noise data sometimes, and we can analyze them using tools from the harmonic analysis. Thank you so much for having me.
Thank you so